Okay, so now I will talk about the greedy search technique we've implemented for the project. The design decisions behind this technique is to use a reverse-specific heuristic to evaluate the quality of all the actions that are to be executed from the state. And for each state, we just execute the action with the highest heuristic value among all the list of possible valid actions. The challenges we have for implementing this technique is mainly due to the time limit of executing an action that restricts the time for us to calculate the heuristic. And the potential improvements of this technique is to incorporate more game theoretic methods to build a better heuristic or tuning the weights to find a better heuristic. Let's look at the demo of two greedy agents competing against each other. As we can see now, both of the agents are reluctant to occupy the sub-corners, which are these four corners, and they tend to occupy the four corners in order to win the game.
Now let's take a look into the second technique we use, which is deep Q-learning. In deep Q-learning, it simulates a number of games and learns the features from them by itself. Here, the agent 0 is the deep Q-learning agent and the agent 1 is the opponent. We can see that the agent 0 managed to get all the corners and all the chases on the edges and the corners are black by the end. Now let's see another game. In this game, the deep Q-learning agent is black. We can see that at the beginning the number of white dices is less than the number of black dices. It's interesting to see that the deep Q-learning agent doesn't own its own, and we can see that it really wants to get to the edges to occupy positions that are not very easily to be reversed.
The another agent we used is applying the Monte Carlo Tree search to this game. Monte Carlo Tree search can help to choose the nearly optimal action. This action may not increasing the score currently, but it can help to get more score in the future gaming step. Let's watch the replay, and agent 0 is our MCT agent. Here's a fun fact that the score is lower than agent 1 initially, but in later game, it flipped a lot of black disc and win this game. MCTS have the best performance in our agents, but there are still some challenges like to build a tree. We need to predict action opponent will choose, and its time cost is quite high compared to our other agents. To solve the challenge of MCTS, firstly, we choose the random for simulation. Its time cost is small, but it always gives an unsuitable reward. And we change to the semi-random, which randomize the action will not make big mistake like choose the action in the sub-corner. But finally, we choose to use the deep Q-learning agent to select our action. Its time cost is a bit larger than random and semi-random, but its reward calculator is more accurate. To let the agent to have better performance, we add some domain knowledge of this game to our agent. The first one is let our AI agent know the importance of corner. Let's see the replay. We add the reward to the action that occupy the corner and add the penalty to the action which led opponent to occupy the corner. And our AI agent can use the corner to flip more disk. Also, when the corner being occupied by our agent, that the disk with the same color in the edge connect to that corner cannot be flipped by opponents. Let's see the effect. We can use this strategy to gain more score, which is stable. Besides, we add a reward for the action to restrict opponent's move. Let's see the effect. As the agent 1 only have a few moves, he placed the disc on the sub corner, which help us to occupy the corner to win this game.